So here we are back with integration, our chapter on integration. We're in section 2. This is the second part of section 2, where we're looking at the area model and using this to get ourselves into this idea of integration. So where we left off, we were looking at this example. Actually, let's go back one. We're using this idea that the area of, we can approximate the area under a curve. Quit doing that. By finding the sum of all of the inscribed areas is the lower boundary, and the area of all the circumscribed rectangles, those were the upper boundary, and the area is somewhere between there. We did that with this example here, and this was all of our lovely work, where we used the left hand side of the rectangles to do the lower limit and the right hand to do the upper limit, and we found our area was between 9.6875 and 11.6875. So where can we go from here? Get another theorem. This idea, again, we saw that with that other example. If we get the idea, we're looking at the sandwich theorem here. If we can make the more rectangles we have, the bigger n gets, the closer and closer the lower limit is going to be the upper limit, and that will get closer and closer to what our actual value should be. And so what we're going to do is we'll take the interval or the limit as n approaches infinity, and we could do that of the lower limit. We could do it as the upper limit. Doesn't matter which one. Either one we should get. They will squeeze together to give us the value that we want, which is the actual value. So we say f is continuous and non-negative on the interval. We have to be non-negative for this to work. So we take the limits as n approaches 0. Both the lower and the upper sums exist. They're equal to one another. And again, our delta x is we're breaking it into equal intervals. So we take b minus a divided by n, and the minimum and the maximum value. So here's where you knew we couldn't get too far without bringing limits back into it, because we said back in chapter 1 that we take these, calculus is basically taking these pre-calculus ideas, static situations, and then applying the limit process to deal with a more fluid, a non-static, a changing situation. So again, we need this limit process to move us forward. But here's the other thing that kind of helps us. If we have the lower sum and the upper sum are going to be basically sandwiches in and gets us to that one value, if this is based on the smallest value on each interval, and this is based on the largest value on each interval, I can pick any value in between the smallest and the largest, and that should still work. So the idea is I can pick a C sub I. I can pick a point that's the easiest for me to work with. I don't necessarily have to I don't even have to know what the minimum value is on that interval or the maximum value on the interval. I just need a point on that interval. And this limit process is going to say it's going to get squeezed between those two, and it will give us the same answer I want. So how do we find? Here's our formal definition. Definition of the area of a region in the plane. We have to be continuous and non-negative. Again, continuous has always been important to us when we're doing derivatives, but we also have to be non-negative because we're looking at the area underneath the curve, between the curve and the x-axis. And when this goes down negative, that's going to cause us problems. And we'll deal with that in later sections. So we're on a closed interval. And the area bounded by the graph and the x-axis and the vertical lines at A and B is going to be the limit as n goes to infinity of the sum as I goes from 1 to n of the function at c sub I. And this is just some value inside each of those subintervals times the delta x, where delta x is b minus a over n. And we just picked this to make it easy and convenient. So let's look at this and give this a try. F of x equals 3x squared plus 1 on the interval 0 to 2. So again, here is my 3x squared plus 1 on my interval 0 to 2. I want this area in here. Whoops, undo that, undo that. So the main thing is I can find easily the things I'm going to need are delta x. And delta x is going to be 2 minus 0 over n, which is going to be 2 over n. I need to figure out what's my c sub I going to be. So I'm going to pick some subinterval in here. Okay, there we go. And so this is my ith interval. I want to pick some point in here I can easily pull off. And I can pull any point along here. Now this is always increasing, so that's kind of nice. When we were doing those before, we always found the right endpoint was a convenient, easy one to find, especially since we're starting at 0. So I'm going to make my c sub I going to be I times delta x. So that's going to be 2I over n. And that's going to pull off my right end of each of my rectangles. And that's between the two endpoints. We can include our endpoints when we do that. This is just a convenient number for us to pull when we're pulling into our formulas. So we are going to need to find the limit as n approaches infinity of the sum as I equals 1 to n of f of c sub I times delta x. That's our definition. That's what we need to plug in. Here's our f of x. Here's our delta x. Here's my c sub I. So we can plug that in and go to town. We'll stay with that color for right now. So again, here we got the best of both worlds. We got a limit and a summation. I equals 1 to n. And f is going to be 3 times x squared plus 1. And x squared is 2i, or x is 2i over n. And we have to take this times my delta x, which is 2 over n. That's the limit we need to evaluate. So before we can evaluate the limit, we got to deal with the summation. And first thing I'm going to do is say, here's a constant. Again, when we're looking at this sum, n is a constant in the sum. N is the variable when we get to taking the limit, but we're not doing the limit yet. We're working with the sum. So in that case, n can be considered the constant. So we're taking the limit as that n goes to infinity, but we can go 2 over n times the sum as I equals 1 to n, well, I can do this, can't I? 2I over n squared was going to be 4I squared over n squared. So 4 times 3 is going to be 12. So we got 12I squared over n squared plus 1. And this again we can break up and deal with. So now we go into our, we're still working with our sums. Limit as n approaches infinity. I got 2 over n. And when I look at this first one, again, in the sum, n is a constant. So I can go 12 over n squared times the sum as I equals 1 to n of I squared, plus the sum as I equals 1 to n of 1. Oh, don't forget, like I was just about to do, we're doing this limit, n's going to infinity. We got 12 over n squared times n plus 1 times 2n plus 1. Give myself just a tad more room here. Over 6 plus, we look at this one, I equals 1 to n of 1 is just going to be n. Well, first thing I'm going to come by and say, hey, 6 can go into 12, giving me a 2 there. And I have n here, so I can cancel out one of my n's. So now I'm doing the limit as n approaches infinity. We have 2 over n times. So this was, we did this before, 2n squared plus 3n plus 1. And that's being multiplied by 2. So we have 4n squared plus 6n plus 1 over n plus 2. And then we have an n here. And now I could, again, combine this all together and play my other games, but why? Let's look at my limiting here as well. Yeah, why? I'm going to multiply this through. Limit as n approaches infinity of 8n squared plus 6 plus 12n plus 4. This is all over n squared, so I'm just going to say n squared, n squared, n squared plus 2 over n times n is going to be 2. And these can cancel out. And one of those will cancel there. So I'm looking at the limit as n approaches infinity of 8 plus 12 over n plus 4 over n squared plus 2. And as n goes to infinity, that goes to 0, that goes to 0. I get 8 plus 2 is 10. So the area under the curve is going to be 10. Now, this is where I said, it's important to be able to use those formulas, because being able to take your calculator and pull in a number does nothing when you're taking the limit as n approaches infinity. So these are the type of work, the type of problems that you're going to get the joy of working with right here. This is where we can take the limit process to take these ideas of making the rectangles, breaking this up into rectangles, and we do this until we get enough rectangles so we get a good approximation of the area underneath the curve. Yay, right? Okay. Let's take this back up to full screen. Last thing I want to talk about is the midpoint rule. We can use this idea of when we have those of making a tangent line to approximate the area. So let's go back to I think it's this one here. The idea of this, we can get rid of that, is if we just say, oh, let's approximate each of these with a straight line segment and go halfway between and make our rectangles there. And this little point that gets cut out is about the same as that one that's added on to it. And if we just use the midpoint here to find these rectangles and make them that way, you can get a lot closer approximation. And that's that idea. Oops, I gotta get off this. That's the idea of the midpoint rule. So we find the area. It's an approximation. A better approximation than finding the lower limit, the upper limit, is we find this middle point. So we just take the average of the two psi ends and evaluate the function at that point times your delta x. This is actually a nice way to do it if you are not doing the whole limit process. You're just trying to draw some rectangles. We can often get by with fewer rectangles when we do that. So for this example, we go x squared plus 4x on this interval. And I want 4 rectangles. So my delta x is 1. These are my 4 rectangles. I'll go halfway between 0 and 1. So I'll do at 0.5, 1.5, 2.5, 3.5. And then I will just plug these 4 values into f and add them up. I'm only going up to n equals 4, so it's not that hard to work out those 4 different values and add them together. So I do f of 0.5 times 1, f of 1.5 times 1, f of 2.5 times 1, f of 3.5 times 1. That's going to get you a pretty good approximation. So this is the one. Again, when we want an approximation, we're not making as many triangles or squares, rectangles. I don't know what I'm talking about anymore. Not as many rectangles. We can often do this, and it kind of error averages out. And again, it's not going to be exact. It's an approximation. But this is another way that we can approximate this area under between the curve and the x-axis. So here are your problems that you can play around working with this. Enjoy.